Okay, so hi everyone. Today I will be talking about solutions to problems A to E and from yesterday's round. Sorry that I wasn't able to stream it live, but well, I just wasn't able. So yeah, I solved A to E on contest and where am I? I'm probably somewhere around here. Yes, here I am. So yeah, as you see, it took me quite a lot of time to solve E, but on other problems I was, well, maybe not super fast, but pretty fast. So let's talk about the solutions. So problem A. So in problem A we are given an array. So let's say this array. And in one operation we can split this array into two parts. Let's say here. And swap those parts. That would mean that this part would go here and this part would go here. And it would form an array like this. Right? Because I would put this part to the start and this part to the end. And we want to say if after some number of operations like this we can make our array sorted. Okay, so basically this is problem A, so it's easy. It was supposed to be easy, but if our array is sorted, so if it would be like this, then our answer is yes. Right? But let's say that our array is not sorted. And now let's look at the first position such that we have like an inversion, right? It means that let's look at the first position such that AI is greater than AI plus 1. So now the observation is that after some number of operations, let's say that, well, we would do this operation and then we would like, let's say, do operation like this. Right? So we can notice that the only array that won't have this inversion is the array like this. The array when this 2 is the first number and this 9 is the last number. So basically we can check if after making this observation our array will become sorted, and well, that's everything. We are looking for the first inversion. We then will make this operation, so we'll just make this operation and check if our array is sorted. Right? Yeah, that's basically it. Okay. So now to problem B. So in problem B we are given an array. Let's say like this, 71935. This was problem A. So in problem B we are given an array. And we want to pick, we say that the array is good if we can pick two such numbers from this array. So in this example we could pick, let's say, 1 and 3, such that every number from this array is divisible by at least one of those two numbers. That means if we pick some number, let's say 9, 1 will be divisor of 9 or 3 will be divisor of 9. The array is good, I repeat, if there exists such two positions in this array that if we pick them, they will, either one of them or maybe both of them, will divide everything else in this array. Right? So I hope everyone knows what divisor is. Cause 3 is a divisor of 9, cause, well, 9 divided by 3 is like natural, right? But 3 is not a divisor of 5. Okay. So now the observation is that one of those two numbers must be a minimum value in the array. Because if we'll think, let's say that we sorted our array, and now we can notice that the only divisor of 1 in this array will be itself. Because, well, my divisors are smaller than me or maybe equal to me. That means that the only divisor of minimum in this array is itself. So one of those numbers will always be minimum, right? So now what will happen? Well, this is a bad example because 1 will divide everything, but let's say like here, this array here. Let me just write it. So in this example here, wait. If we sort our array, we get 2, 3, 6, 4, 12. So, well, we have to pick minimum. And what this minimum does, it, deletes some elements from the array. Right? Because we can say that all of the multiples of 2, we can delete them from the array. Because, well, we just need to satisfy that they will be divided by at least one of them. So if they are divided by this minimum, then we can delete them. So 2 will delete itself. It will delete 4, 6 and 12. And in our array will remain only 3. But let's say that there were also like 15, 30 and 45. So now another observation is that, well, we just have to take the minimum from this array, right? It's the same observation as here. The only divisor of this thing is, well, the minimum of this array. But you can ask why there can be a situation like, well, this 2 divided something here, some x, and x divides 3. Well, then 2 would also be a divisor of 3, right? So here we also need to take the minimum. Because, well, as I said before, my divisor must be smaller than me. So I take the minimum and check if in this new array everything is divided by minimum. And that's it. So yeah, that's it. Yeah, you can't ask questions on chat, that's bad, but I'm sorry. Next time, today I will do like a normal stream. Okay, but I hope you understand. So to problem C. Okay. So problem C. Okay. So in problem C we are given some array. And in one operation I can pick an interval from this array and replace all of the elements on this interval with its median. Let's say that, well, median from the interval 4, 3, 5. Median works like this. We take the values from this interval, sort them, and we pick the middle element. If we would have like, let's say, 6 here, then we would get like 4, 3, 5, 6. Then we take like the first of the middle elements, not the second. Right? Okay. So we take the median and we replace all of them with median. Here median would be 4, because, well, it's the same as here. So we would be like with 4, 4, 4. Then we could pick this interval and have like 1, 4, 4, 4, 4, 4, and pick this interval and have like all 4s. So now in our problem, they ask us a question like this. After some number of operations, we want our array, all of the elements of our array to be equal. What is the largest value that those elements can have? Right? So here it would be 4, because we can make this array all 4. But for example, we can prove that we can't make it all 5. Right? So, yeah, that's it. So our observation is like this in problem C. If we have two numbers of the same value, so let's say xx, like next to each other, they are on adjacent position, then I say that we can make all of our array equal to x. How to do it? Well, we can just, grow our farm of x's. We can pick we can pick any interval of size 3 such that it will contain only x's, right? Such that at least 2 of values on this interval are x's, and we are assured that the middle value of this interval will always be x. And then we can grow it like this. Then maybe I will grow it like this, and we can notice that, well, we will be able to fill our whole array. So now we want to have two adjacent values like adjacent to each other, right? Two same values adjacent to each other. So well, if there doesn't exist, let's say that we look at some value x. So now I won't prove it because I'm not sure how to prove it, but I think you can think about it. Now, if there isn't any interval in our array such that its median is x, I say that any interval, of course, of length longer than 1, because, well, we can just pick x. If there isn't any interval of length longer than 1 with median x, then we can say that, well, x, our array can't be set to x in the end, right? But of course, if there exists some interval of length longer than 1 with x, then we can just use it and have two x adjacent to each other and make our whole array filled with x. So now our problem is like this. Find the interval with maximum median in our array. So I will first show you like the concept that is sometimes used with tasks about median, and then we will do some observations and do it easier. So we can do bin search over median. What does it mean? Let's say that we want to check if our answer can be greater or bigger than k for some given k. Then what we can do? Well, we can if we have some AI that is at least k, then we say that our bi is equal to +1. And if we have some element smaller than k, then bi is equal to 1, -1. How would it work? Let's say that we have array like this, 1, 2, 3, 4, 5. And we want to see if there exists an interval with, let's say, median bigger or at least 3, right? Our 1 and 2 will be set to -1, because they're smaller than k, and all the other numbers will be set to 1. Do you see what now we want to find on this array, new array, on array B? Well, now we want to just find if there exists an interval with sum greater than 0. And this is a standard prefix sum task or something. But now let's notice that if we have some interval with sum greater than 0, right? Let's say interval like this. Then we can always divide it into intervals of length 2 and 3. This is true for every interval with sum greater. This is true with every interval of length greater than 1, that we can divide it into sub-intervals of length 2 and 3. Right? So we could divide it like this. Let's say that we have an interval of length 9. 9 numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so how to divide it? Well, we could divide it like here, like this, let's say. So if our sum is greater than 0, then it's obvious that at least one of those intervals will also have the sum greater than 0. Right? Because if all of them would be at most 0, then well, their sum would be at most 0 too. So now we have shown that if there exists an interval with sum greater than 0, there also exists an interval with length at most 3 and sum greater than 0. So basically what we have shown now is that, well, we can just, our answer will be just the greatest interval with size, it will be among all intervals with size 2 and 3, it will be the greatest median of all of those intervals. Right? That's what we have shown with our bin search proof, which is kind of nice. So if we would look at our examples, here we have only one interval with length at most 3 and bigger than 1. And this is interval 1, 2. We see that median of it is 1. Because as I said, we have, as its length is even, we have 2 middles and we always take the first one. Here we have interval 1 to 3, many uninteresting intervals, but we can notice this interval 4, 5, which has length 2, which is good for us, and it also have median 4. So this is our answer. So maybe here I will show you my code, if someone didn't understand. We're reading our array, and then I'm iterating over all intervals of size at most 3, right? Because interval I plus 2 will have size 3, so I'm iterating at most to I plus 2, and well, I'm sorting this interval and looking for the median and maxing out the result. So yeah, that's basically just it. So Now to problem D. But, you know, this problem and the same with problem A, you could just guess it, I think. Like, I don't know, you could look for the examples or something, or if someone knows this bin search, then the idea is obvious. But here you could just look on the examples and see that, oh, it's sorted, or it's like bitonic, or no, it's not bitonic. It's like, well, it's like two sorted arrays, but like put it together. So, well, you can just guess the solution from the samples, but it's not good. And the same with paint the tree. Like here you don't guess from the samples, but you have like an idea, which I can prove it, but not like, you know, not like strictly. I can just, you know, say that intuition behind why it works. But now to problem D. In problem D we are given a tree. Let me write a tree. I wrote something bad, I think. Oh, cause this is not edge. I'm sorry. Okay. And we have one vertex marked blue. This will be vertex 5. And one vertex marked red. So, now in one move, we have one blue chip placed on vertex 5 and one red chip placed on vertex 4. So now in one move we can move the chip we have to move both chips to the adjacent vertices. And what is happening? Our blue chip is marking our vertices blue, right? So, and then when our vertex is like our red chip is not doing anything unless it will go to some vertex marked blue. If it would, with this path, it would go to this vertex marked blue. If it goes into some vertex that is marked blue, then it marks it red. Right? So, first a blue chip must go into some vertex, mark it blue, and then after it, when our red chip will go into it, then it will mark it red. And our problem asks us what is the minimum number of turns that we need to make to mark the whole tree red. So, one observation that when I was thinking about it I made is that, well, before they meet, like they have to meet, let's say, or like cross path, before they have their paths crossed, red vertex can't really color anything, right? Because, well, red vertex have to be somewhere, as red chip has to be somewhere second to color it red. Okay. So, well, we want them to meet as early as possible, right? Because if they would meet, let's say, in 8, right, I would have my blue and red vertex here, then they could like go together everywhere and like meet the tree together, or like go through the tree together. So, well, as we want them to meet as early as possible, they will meet in the middle of their path, right? And well, if we have this vertex, it may also be 2 vertices, but we'll go into it. Then now we have a problem like this. We have some vertex, let's say that it's our root. We have both of our chips here. And in one move, we can move both of our chips to some vertex and color it red. Right? Because this is, if we move them together, this is what will happen. So, what is the minimal number of moves that we need to make? Observation is like this. We will go into every edge and out to every edge. So we'll traverse each edge 2 times, except from the edges alongside the path from root to the vertex that we end up in. Right? So our answer will be 2 times number of edges, so n minus 1, minus the depth of v, minus the depth of the vertex that we end up in, right? Yeah, this is basically our answer. So, well, we won't go out of the, we will go into the every edge, but we won't, and out to every edge, but we won't go out of the edges on this path. So we see that it will be always optimal to choose the maximal depth. So, what will our answer be? It will be length of path divided by 2 plus 2 times n minus 1 minus the depth from v, where v is from the vertex that we end up in. So here it will be 4. But it wouldn't be optimal. It would be optimal to end up in 2, because we see that it's like deepest out of all vertices. Okay. So, now, we see that we will find the middle of our path between them and calculate this maximal depth. But what if our path is like, here our path is nice because it's like it has even amount of edges. But what if our tree would look like this? And we would have our vertices like this. Here, well, what would be our middle of the path? This or this? Well, what will be the first vertex such that the red chip will go there as a second chip? Well, it will be the vertex 3. So we can always take like the farther vertex, because before the red chip will go to some vertex as the second one, nothing interesting will happen. So we can just do it like this. So it's like not a formal proof, but I hope everyone understands. It's just some, we'll do one DFS to find the path between them, And then another DFS to find the depth of the tree rooted in vertex V, and vertex V is this middle. Okay. So I hope I'm not going too fast today. Yeah, but I can't see your questions on the chat, so I'm sorry about that. So now problem E, which was the problem that, well, it took me a long time. So problem E. So in problem E, we are given some tree. And I will say that initially all of the vertices of the tree are black. You have like different colors in the... well, initially some of the vertices are red. And some of them are black. You have different colors in our task, but, well, it won't make us a difference. And in one query, what you do, you toggle a color of a vertex. So for example, I could pick this vertex, and as it's black, well, it will become red. But if I would pick this vertex, then it would turn to the opposite color, so from red to black. So now, after each toggle, we want to say, are the red vertices currently forming a path? So for example, this is a path, but this is not a path. Because if I would like to draw a path between them, there would be some some black vertex here. And for example, this is not a path too, because, well, this vertex has a degree of 3. So it's impossible to draw a path between all of those vertices. The path that goes through all of those vertices. So, yeah, we want to, after each toggle, we want to identify if we can, if they form a path, right? Okay. So, how to do it? There is some solution with degrees of children or something I saw in Eddie, but I have different solution, which is also nice. So, if our red vertices form a path, then there must be some starting vertex of the path and ending vertex of the path. If somehow I could fastly find those two vertices, then now what I would need to check? I would have to check if, let's say that I have found U and V, right? Here it's U and here it's A and B. Let's say that I have found A and B. So, somehow, I will later tell you how. Now, what I would like to check is, I have the conditions like this. First, length of path from A to B must be equal to number of red vertices, right? Because well, this path can only go through red vertices, and so it must go through all of the red vertices. 2. Number of red vertices on this path must be equal to its length. Why do I need this second? Why do I need second condition? Cause well, here, for example, I could identify this as A and this as B. So we see, well, length of this path is 3, as I said. But it's not a good tree, because not all of the red vertices are on this path. That's why I need the second condition. So now first, let's focus on how to find A and B. Right? So, to find A and B, well, we have two separate. We have two separate. We have like two separate cases. Oh yeah. First case is like this. Our red vertices form a path like this. It's not like, this. It's a path when every vertex is a direct sum of its previous vertex. Right? So here, what we would like to find is our vertex with smallest depth and biggest depth. So we can keep the depth of the vertices on some set, right? Yeah, I will later show you my code. But the second case is like this. Our vertices form a path, but it have like this, it's like built from like two paths, like this, right? It have this LCA that have like two children. So here, what we would like to find, we'll like to find the vertex with the to solve this task, you have to know the pre and post order. When we will do our DFS, we can keep the time in which we are going into some vertex and out to some vertex. So we can see that this vertex will be the vertex that will go, that will leave the first. So it's the vertex with the smallest post. And this vertex, so our B, is the vertex with the greatest pre-order, because it's the vertex that we go into last. So, and here we can notice that this vertex A will have it will have the smallest post and also the biggest pre. So we find the vertex with smallest pre, with biggest pre. We find the vertex with smallest post order, and if they are the same, if A is equal to B, then we are doing this case with depths. Right? Otherwise, we just have them. Right? So here we are doing depths. And here we are doing pre and post. I can write it for you. A is equal to vertex with smallest post order. So the vertex that we leave the first in DFS. Vertex that we in post order, and B is equal to vertex, maybe I will write it like down here. So A is vertex with smallest post order, so we'll keep them on sets, of course. The vertex that we leave first in DFS, and B is vertex with biggest pre-order. So the vertex that we enter last in DFS. Notice that here we have leave and here we have enter. Right? This is the vertex that we leave first, and this is the vertex that we will enter last. And if A is equal to B, then we have path like here, then we have the simplest path, and we have to look at depths. Depths. Okay, so we found A and B. Now how to check our conditions? This is a good question. Well, first, condition 1. We can of course keep in some variable the number of red vertices that we have. This is easy. To find the length of path from A to B, it's an easy task with jump pointers and LCA. I hope everyone knows how to do this. I think there is even a tutorial on Cheyenne channel. I hope there is. So yeah, we find LCA and the length of the path. We'll use, in this solution, maybe I will, copy it down here because I will have more place. In this solution, we will be using pretty known formula. When we want to find the, let's say, length of a path between this vertex and this vertex, let's say that we have calculated array depth. It means what is the amount of edges on the path from root, so let's say R, and our vertex V. Right? So, what is the amount of edges on, well, let's say that our root is here. What is the amount of edges on the path from vertex A to vertex B? Well, it's this path, so depth from B, plus this path, so depth from A. But, well, this edge, it's not on their path, but it's calculated twice. So it's 2 times depth of this vertex, this here. But this vertex is just their lowest common ancestor. So minus 2 times depth from LCA. So yeah, we just have to find LCA, calculate depths, and we have the first condition. We can check it in like log of n. Now the second condition. It looks like you can use heavy light decomposition to get like log squared, but I don't think that it would work. It would have too big complexity. But you can do it faster. How to do it? You want to have some structure that gives you a tree, and in one operation you can either choose a black vertex and make it into red vertex, choose a red vertex and make it into black vertex, and get a path and ask, and it will allow you to answer a question of the form: how many red vertices are on this path? Right? Okay. So, well, let's do the trick that I show you here. Instead of counting the red vertices on this path, we'll count the red vertices on the path to the root. So it will be, let's say, red from A, right? So the number of red vertices on the path from A to the root, plus red from B, the number of red vertices on the path from B to root, minus 2 times number of red vertices from the LCA to the root. But we also have to add here, because, well, okay, I have added all the red vertices here. I have added all the red vertices here. And I have subtracted all the red vertices here. But what if root is red? So I also need to add plus 1 if LCA is red. LCA is red. This is when I add 1. So now we would somehow want to keep our array red, but we want to keep it with updates. Remember, we can't pre-calculate it like depths. We want to toggle a vertex and somehow pre-calculate array red. How to do it? When I have my tree, and let's say that I change this vertex to red. For which vertices, or let's say that I change this vertex to red. For which vertexes our array red will change? Well, certainly not for this one. Not for this one too, because we only look on the path from me to root. Not for this one. Well, the only vertexes such that my path to root will go through me, those are just the vertexes in my subtree. So what I want to do, I want to add 1 to all of the things in my subtree. And this is a standard segment tree problem, right? Or maybe, well, now I will toggle it and it will change to black. Well, okay, now I want to subtract 1 from all of the things in my subtree. How to do it? We can keep a segment tree, like segment tree add-on interval find a sum in point. And in this segment tree, we will numerate it by pre-order of this tree. If you will look at this subtree, all of the vertices in this subtree will have the pre-order from the pre-order of vertex v to the pre-order of the last vertex in this subtree. This will be just pre-order of vertex v plus the size of this subtree, because, well, I will go in my DFS through every vertex of this subtree, minus 1, because, well, now this interval have the size of the subtree. If you will, you have to subtract 1. And that's basically it. So we find A and B using pre, post order, and depths. That's why we need like 3 sets. So this is not like a super fast solution, but I have, if you will look, I have like I have like half of the time, so pretty safely. And having those vertices, you have to check those 2 conditions. Using LCA and depths, you check if their length is equal to the amount of red vertices, and you check if all of the vertices on this path are equal to its length. If all of the vertices on this path are red, so the number of red vertices on this path must be equal to its length. Right? Right. And yeah, I will show you my code, because I don't know how to say it in English. Like, I think it's good to implement this, because those are some, pretty standard techniques. So here I'm doing some DFS, calculating pre-order, post-order, sizes and depths, also jump pointers. Here I have my function that calculates LCA, right? And yeah, here I have my segment tree. That's just a standard segment tree. Here I have those 3 segment sets. Here I found U and V and check those 2 conditions that I set to you. This is exactly the formulas that I wrote. This formula is the formula here, and this formula is the formula here, as you can see. I of course update my sets, and as you see, I numerate my segment tree using pre-orders. The same here, right? Because it allows me to easily update the subtree. And yeah, basically that's just it. Just some techniques put in on top of each other. Maybe I will like scroll through this slowly. Or I will just put the link in the description to the code, yeah. I will just do this. Code share or something. I don't want this to expire. Wait. There was like one code share apps. There was like one when you oh, here. I will find it. I just need a minute. Well, I can do it in ID1. Yeah, this is maybe not so stupid. Yeah, okay. And now how to oh, yeah, this is this. Okay, so I will give you this link. Maybe I can even put it here so I don't forget. Yeah. So thank you for the stream. I will, as you see, I will stream today a Div 2 round, so be there and see you next time.